Hi, my name is Collin Turk, and today I'm going to be talking about fusion energy and why it is the best thing to invest in this century. With rising gas prices, limited fuel reserves, and the destabilization of the environment, developing technology that utilizes other forms of releasing potential energy is becoming more and more important. We need to develop new technologies and utilize them if humanity is to survive the century. I recommend we all invest in the bright future of fusion energy. In the last few years, the fusion community has developed some very innovative solutions to some of the most challenging problems science and engineering has ever had to face. Some of these solutions have reinforced the idea that fusion power can pave the way to a future with a virtually limitless supply of clean energy. By investing in fusion power, we can break away from non-renewable energy sources and power the demands of the growing population without destroying the environment. Today I will be talking about what fusion energy is, why it's worth investing in, how we create it, and the types of projects that are currently underway making fusion power. So what is fusion power? Fusion energy is the energy of the sun and the stars. The sun is made up of mostly hydrogen atoms, and these hydrogen atoms are existing in a plasma state. Unlike a gas, in a plasma, electrons and their respective nucleuses will move freely from one another. They're not bound by their electron orbitals. Now, when pressures and temperatures are high enough, some of these nucleuses will fuse together to create heavier elements. Now, when these two nucleuses come together and fuse, they lose a small amount of energy, or a small amount of mass. And that mass, because of the famous Einstein equation, E equals mc squared, that mass is directly converted into energy. And not just a little bit of energy. Now, the most promising type of fusion reaction is the DT reaction, which is the deuterium and tritium reaction. This image is provided by Tokamak Online. If you look closely, you'll see that deuterium is just a hydrogen with an extra neutron, and tritium is a deuterium atom with another neutron in it. When these two fuse together, they create a helium atom, but it has one extra neutron. So it shoots off that neutron, which gives away 14 megaelectron volts of energy. And the helium atom becomes an alpha particle, which you can directly extract energy from, which releases another 3.5 megaelectron volts. Now, most people don't think about energy in megaelectron volts. So, to give you an idea of how much energy is created when you fuse these two isotopes of hydrogen together, is if you were to take 1 tablespoon of liquid deuterium tritium and you were to fuse it all together, you would release the same amount of energy that is in 28 tons of coal, or 143 barrels of oil. A fusion reaction is 11 million times more efficient than any chemical reaction. So, how do we propose to create fusion energy? Well, first, what we have to do is we have to combine this plasma, because the electrons and the nucleuses are not bound by their orbitals. The nucleuses will want to naturally repel each other because they have like charges. They're both positively charged. So because of that, you have to force them together to cause them to actually fuse. Now, if you use a magnetic field, charged particles will spin in corkscrews around the magnetic field lines. This will prevent the plasma from touching the walls. If the plasma touches the walls, it is at an extremely high temperature. We're talking 80 million plus degrees Celsius. If it were to touch the walls, it would melt it instantly and destroy your reactor. So the most common way to achieve this is with a reactor design that's called the tokamak. And in a tokamak, plasma will spin inside of a toroidal, like donut-shaped magnetic field. This solenoid here too will add additional energy in this area where the plasma will spin around and around, following the electron orbitals. Now, as the temperature is increased and the pressure is increased, the plasma will start to fuse, and the neutrons that shoot off of that reaction will hit these outside collector plates, which will then create a temperature which you can extract with a liquid coolant and use to heat up steam, which will then turn a turbine. There is another problem though with on the insides of these. If your plasma does arc or touch due to an instability, it will melt, even the most heat resistive of metals. So one way that they've been able to here recently stop that problem from happening, because we've had these reactors for over 50 years, but they've never been commercially viable. But in the past few years, we've solved some of these solutions, and one of them is the cooling problem. If you release nitrogen into the plasma by the edges of the walls, because nitrogen has 2 electron orbital shells, instead of existing in a plasma state where the electrons and the protons and neutrons are separated from each other and move freely, they will actually hold together their orbital shell. And the energy will bounce back and forth between these electron orbitals, which will shoot off photons. Now, photons go in all different directions, so that disperses the heat evenly rather than in a localized area where it would then melt whatever edge it touched. If everything isn't completely smooth on the inside of this, you will create a collection area which will then melt it, and the plasma won't be uniform. Now the other thing we have to do is we have to withstand this heat, because even with the cooling and the magnetic confinement, the amount of temperature that's in this sort of donut-shaped area has to be released in some way. And that means you have to have all of your walls made out of tungsten, which has a melting point of 3,600 degrees. You also have to dissipate the heat in the reactor vessel, and it has to be dissipated evenly. So that's where the nitrogen cooling comes into effect. The next thing you have to do is you have to shape the plasma, which means you have to destroy the magnetic field a little bit near an area of instability. You do this using external magnetic coils. And this creates a different localized flow, and it prevents electromagnetic instability through these interacting magnetic fields. Now when the plasma is too close to the wall, you can push it away with another field with more density of magnetic pressure. This creates a plasma flow that follows the least resistance. Now, what type of fusion reactors are currently being worked on? Well, the most common, and I've used this earlier, is the tokamak design, with the spinning plasma inside of a donut-shaped magnetic field. But if you look closely down here, this is the ITER International project, and it is a fusion project currently being developed, and that right there is a person. This thing is a huge piece of machinery with very, very complex and precise components. So fusion is hard and expensive as of right now. But there are other types of fusion reactors which have been produced, which show some promise, but need investment. One of those types comes from Lockheed Martin. where you use two superconductive magnets to create a plasma stability zone where you can then fire neutral particle beams into the middle and extract energy by heating up the walls with those neutrons that are flying off, and then running that through a cooling system and then into a heat exchanger, which then turns a turbine. But there are also other types of reaction besides the DT reaction. The DT reaction is the easiest to produce, and it produces the most amount of energy per fusion. But there's some problems inherent with it. One is that the neutrons carry 80% of the energy, and neutrons are nasty. When they hit objects, they still want to bounce out and create a new form of... Essentially, they become radioactive. So then there's waste to deal with. It's not as bad as fission reactor byproducts, but it's still radiation and has to be contained and stored for periods of time. But there is a different type of reaction, which is called the boron fusion. Boron fusion takes a boron-11 isotope, which has one extra neutron in it, and it slams a proton into it. This temporarily creates carbon-12, which then splits into a helium atom and a beryllium atom. And this beryllium is inherently unstable, so it will then split into two more helium atoms. But the total number of protons and neutrons are the same. So what this means is that no extra neutrons are flying off of this reaction, and that means the helium atoms carry all of the energy of the reaction. Because of this, this is a direct translation into direct energy. When a helium atom strikes a conductor, it will carry that charge directly without having to use a heat exchanger. One type of reactor that is currently being worked on but is completely underfunded is the Polywell reactor, which uses 4 different superconductive magnets that create an electron trap in the middle. They then fire the boron and the proton into this reaction, where they can't then escape the magnetic confinement. As you increase the energies, these electrons escape in the only place that they can, these alpha particles. And that's through these small little gaps between where the magnetic fields converge. And they will hit this positively charged shell on the outside, which will then create the pressure necessary to push the electrons down a wire. This type of reactor has the ability to be completely clean, and because it uses boron and hydrogen, the amount of potential fuel that we can use is virtually unlimited. There is a limitless supply compared to how much you actually have to use. 2 teaspoons of this boron, it will create enough energy to send a F-16 to the moon. This is not currently at its operational state because it's only had $10 million worth of funding, whereas the ITER project, which is a tokamak, and what is currently being invested in, costs tens of billions of dollars and gets investments every single year. But due to the nature of having a small company that's a research, like operating a research reactor rather than a final product, and because it doesn't use the traditional DT reaction, there is not as much funding for it, and the people who are funding it are places like the Navy, who then want non-disclosure agreements. If we were to invest in this reactor, it would have the potential of creating energy which is cheaper than any form of energy that we currently create by any other means. This will be especially important if we are to get off of these fossil fuels, to utilize these types of systems that aren't going to cost billions of dollars and be uneconomical, but rather If we invest in these smaller types of innovative fusion technologies, we can create something that has market viability. And that with a few thousand of these reactors at 200 million apiece, we could power the entire world on nothing but fusion reactions. In the last few years, the fusion energy research community has come up with some solutions to the problems that have made fusion energy too impractical and expensive to develop. There's a saying that fusion energy is 20 years away, and it always will be. However, now it appears that the handling of both steady-state and transient heat fluxes is possible. We have proven that creating fusion plasmas are possible, and with devices like the tokamak reactor, we have proven that it is achievable. The next generation of fusion reactors, like the ITER, will demonstrate the scientific feasibility of fusion reactors, but they won't give us energy. So we need to continue to invest in fusion energy if we are to have the future that we want. Fusion is the best answer to the clean, sustainable energy problem, and we must invest in its future if we, as a species, are to have a future of our own. These projects may cost tens of billions of dollars, but they are necessary stepping stones to harness the power of near unlimited energy. Developing functional, steady-state fusion reactors will be the next great triumph of humanity over nature. Short of becoming a plasma physicist and working on these projects yourself, investing in fusion is the best way to be a part of this new frontier in physics that will permanently change the world for the better. So please invest and educate yourself. Thank you.